prove that if f of x is continuous on the interval ab and the interval ab is divided into n equal partitions with delta x is equal to b minus a over n, then the difference between a right-hand Riemann sum and a left-hand Riemann sum approaches 0 as the number of subintervals n approaches infinity. Solution: divide the interval ab into n equal partitions. Here's x0 equals a, x1, x2, x3. These are all delta x units apart. The width is the same as delta x. Delta x is b minus a over n with equal partitions. Here's another way of seeing it. x1 is delta x units apart from a, x2 is 2 delta x units apart from a, xi is I delta x units apart from a, and xn is n delta x units apart from a. We note that xn is equal to a plus n delta x, and that's equal to a plus n delta x is just b minus a divided by n. Cancel, cancel, and the a's cancelled as well, and you just get b. That means xn is equal to b, and x0 is a. So here's a diagram. Here's your function. You can see how the right-hand rule overestimates the function. The left-hand rule underestimates the function. So for the right-hand rule, between every interval you evaluate the function at the right endpoint. That's f of x1, f of x2, f of x3, given by the black horizontal line. The left-hand rule underestimates, so you're evaluating at the left endpoint, given by the red line. So left endpoint of these two is x1, so you're evaluating at f of x1, f of x2, f of xn minus 1, and f of xn. So let's write Rn. Rn is a right-hand Riemann sum. That's going to be f of x1 delta x, that's the area of this rectangle, plus f of x2 delta x, that's the second rectangle, that's this one, plus f of xi delta x, plus f of xn minus 1 delta x, plus f of xn delta x. That's the sum of all these rectangles given by the right-hand rule. So we're just adding up these rectangles. The left-hand rule evaluates the function at the left endpoint. So it starts at x0. F of x0 times delta x plus f of x1 times delta x plus f of xi delta x, and it goes all the way up to the one before the last. So it goes up to xn minus 1 plus f of xn minus 1 delta x. Now let's subtract Rn minus Ln. So Rn minus Ln. You will see that these are going to cancel out. So f of x1 delta x, that's going to cancel this one, and the only thing that remains is this term f of xn delta x and f of x0 delta x. So that's going to give us f of xn delta x minus f of x0 delta x. Now let's factor out delta x times f of xn minus f of x0. But we saw before that f of xn is just f of b. F of x0 is just f of a. And delta x is b minus a over n. This is Rn minus Ln. Rn minus Ln, the difference between right-hand and left-hand Riemann sum. Okay. Now let's rewrite that. Rn minus Ln is equal to b minus a divided by n times f of b minus f of a. Now take the limit. Now take limit as n goes to infinity. So the limit as n goes to infinity of Rn minus Ln, that's equal to limit n goes to infinity, b minus a over n times f of b minus f of a. But b minus a and f of b minus f of a, these are fixed constants. Fixed constants. That means when we take the limit as n goes to infinity, this limit will approach 0. Okay, so we expect this difference between the right hand and left hand Riemann sum to approach 0 because they both represent a definite integral. They both represent f of x, the integral a to b f of x dx. So let's illustrate with a diagram what's taking place for one of the rectangles. So let's say here's your function f of x, and here is xi minus 1. Here is xi. Now with the right hand rule, we evaluate at the right endpoint. So this is, all of this is f of xi. With the left hand rule, we evaluate at the left endpoint. So all of this is f of xi minus 1. Now this difference, this is delta x of course, and this difference is going to be f of xi minus f of xi minus 1. So you can see how essentially the sum of these differences will approach 0 as n goes to infinity. Okay, thank you.